So in this section, so in wind tunnel we have various components, that is large ducts are carrying throughout the flow channel. So it is nothing but a simple flow channel only, but inside the flow channel air is blowing. The losses occurs, that is energy losses of the wind tunnel should be maintained. That is, if we are considering energy ratio, the energy ratio of the wind tunnel should be maintained always less than or equal to 1. So this is the maximum possibility of case. So in order to bring down this energy ratio, we are considering losses. So how energy losses happened? If it exceeds, if this energy ratio exceeds 1, so there is some losses in the section. So we have to consider the losses for calibration purpose or calibrating any kind of wind tunnel sections. So in today's class we are going to formulate the equations for losses in diffuser section. So now I am considering a diffuser. Let us consider this convergent divergent diffuser. So it is having inlet and outlet. So let inlet velocity be v1 and outlet velocity be v2, and diameter of this particular section will be considered as d1, and diameter of this particular section will be considered as d2. And then the angularity, that is the angularity deflection, is given by alpha by 2. So this alpha by 2 is similar to the another divergent section. And then if we want to consider this d2, so what will be our final d2? So it will be compensated with d1 and this d1. Since the two lines are parallel, we have d1 at this case, and then we have the remaining portion. We have to find out what is this length, so that you are considering length of the diffuser. If we consider length of the diffuser, then this could be solved as, so here it is opposite side and this is adjacent side. So or else this has adjacent side, so where we can actually fix the adjacent side only at the angularity. So this is your adjacent side and this is your opposite side. So according to tan, so tan alpha by 2 is opposite by adjacent. So according to this, we have opposite side, that is L length L, and then it's adjacent side length L, it's adjacent, and then we have opposite. So you are going to calculate opposite side only. So this opposite side is now L into tan alpha by 2. Similarly, this portion is also L into tan alpha by 2. So in total we have d2 is equal to d1 plus 2 times of L into tan alpha by 2. So here 2 times. So 2 times of L tan alpha by 2. And then we are writing the pressure loss equation, which was given by Reynolds friction coefficient. So it is nothing but delta P in general is half rho V square. So this is your delta, and then since it is incompressible flow, you are considering or treating the density. Here is also constant, and here is also constant, and here is also constant. Density we are concentrated throughout the medium. And then what happens to the velocity? So for this, we are initially considering this velocity as v square. Now, what Reynolds adding the friction coefficient is that he adds the minimal amount of friction coefficient occurs inside the duct. So that is residual friction coefficient. And then we use the other term as L by D. So length by diameter ratio. We just usually add it. And then we frame that how much amount of variation will be occurred with respect to part by part, so that he has considering the complete equation as an integral form, as in this way. So 0 to Ln. So that is change in area of the section to section. So that is Ln. So 0 to Ln. And then we have Vn square here. And then the section to section, the length varies. So it is change in section and then divided by diameter at each and every section. So when we look at the diagram, here again I will draw the same diffuser section. So here we are considering section to section. So here it is N. So N describes 1, 2, 3, 4, 5. For varying sections we are considering. So at this section, what is the pressure loss? At this section, what is the pressure loss? Likewise, we are considering pressure loss in each and every section. And then from this, and by considering this pressure loss equation, what we are going to enable is that we have to find out the friction coefficient or pressure coefficient, that is pressure loss coefficient. So this pressure loss coefficient is nothing but pressure ratio. So how much the pressure coefficient it is and how much it losses. So that's our ultimate aim to find out. So it is nothing but K equal to delta B by Q, and you know Q is dynamic pressure. So this is the case we have to deal now. So in this, what we are going to do is, now we are going to simplify this equation. First we are going to solve this equation. We are starting continuity equation, and you know continuity equation very well. So that is discharge at section 1 is equal to discharge at n sections, because we are considering n number of sections. So as of now, you know what is meant by discharge. Discharge is nothing but area into velocity, and then at every sections it is nothing but area, varying area multiplied by varying velocity at each and every sections. And then this area is nothing but cross sectional area, so that again we are simplifying as pi by 4 t1 square v1. Here is also pi by 4 dn square vn, and again these two are getting cancelled. And next what we are going to do, we are going to square this term, squaring on both sides. So finally we are getting t1 power 4 v1 square dn power 4 vn square. So now what we want Vn. This is the actual case. So in order to have the V1 with a reference value, we have only the reference value D1 and V1. That is our reference value. We have to estimate the actual case of velocity in each and every section, that is varying divergence section. So that we have to estimate this value, so that by equilibrium, just you are equating the Vn square is equal to, we have Vn square and then d1 divided by dn whole to the power of 4. Now what we are going to do here, we are going to substitute this particular step, that is you are going to replace this Vn square in terms of your this particular constant value. And after substituting it, again we have to simplify for differentiation of Ln, and then here it is length varying section, and since the diameter is also the diameter variant section, as well as length as well as diameter, but the length here it varies in linear form. So what we are going to do, we are going to change the order of integration from 0 to ln as d1 to d2. So how this d1 to d2 came? So it is by considering dn as the varying term, and it is the integral term, that is, it is the differentiable part. So here for this case, again we are considering this equation. So here this d2 is nothing but varying section. So if we are considering this portion or considering this portion, we are considering this as a dn. So when you are considering this as a dn, you are considering the same equation for simplification. Okay, so here we have dn is equal to d1 plus 2 ln tan alpha by 2. So here we have to consider the similarity. So that is, here you are considering L only, and since this is the length of the section ln means, and here also ln, they are considering the same criteria for this. So when you are differentiating this equation, so differentiation, so ddn, and this is a constant term, so it becomes 0, and finally we have 2 tan alpha by 2, and this ln is also the differentiable term, so differentiation with respect to ln. So finally we got the equation. So that is, we have the differentiable part dln as dn divided by 2 tan alpha by 2. So now what we are going to do, now we have this particular thing. What is that? dln has been replaced by ddn equation, that is the following. dln is replaced by this particular equation, and then we can also replace this vn square, and then we can also change the limit as d1 to d2. So now we are going to find the amount of pressure loss. So how much will be the amount of pressure loss? Sorry. So how much will be the amount of pressure loss? Now we are considering delta P, that is our new equation. Delta P will become as Fn rho by 2, right? So Fn rho by 2, and then instead of 0 to ln integrate, we are going to integrate with d1 to d2, and then similarly we have this equation. So instead of vn square, we are going to rewrite this equation. So v1 square by v1 square, and then d1 by dn whole power 4, and then we have dln equation, the same equation. So ddn by 2 tan alpha by 2. So we have constant term here. So what are all constant terms? So here these things. So here we have 2 alpha by 2, and then d1 power 4, and then v1 square. All things are known to you, so that we are taking these terms outside, commonly outside, and then we have the another constant term. So on neglecting all the constant terms, let us consider this particular constant term as C, capital C, and we leave it afterwards. That is, after integrating, we can substitute this constant term. So this step is, let consider C equal to Fn rho by 2 v1 square d1 power 4. So d1 power 4 divided by 2 tan alpha by 2. So this is your C term. Now what we are going to do? Now we are going to rewrite this equation of delta P. So delta P equal to C. So that is this constant term, and then integrate with respect to T1 to T2. We have the only part that is which are left to you. So from this, wait a second. So dn power 4. So here we have the other term dn divided by tn, so that this dn could be multiplied here. Extra dn term will be there. So after eliminating all the constant, we have dn power 4 and then the other dn. So totally we have dn power 5. So you have to write this equation as dn by dn power 5. Now we are going to integrate this particular term, and you know the formula for integral. So on substituting, we have dn power minus 4 divided by minus 4, right? And then d1 to d2. So upper limit minus lower limit. So upper limit is d2 square, that is d2 minus 4, and then you can also remove this 4 here. You just keep the minus upon the numerator, and then you just shift it. So that is, you just shift it, the negative sign, and then we will execute these steps. Next thing, minus of minus d1 power minus 4, and then our final step is going to end now. So here minus into minus plus, so it is 1 by d1 power 4, and this is 1 by d2 power 4. Since the exponent which is carrying negative will be written as in reciprocal form. So finally we have this delta P equation. Right, now you substitute the value of C. So what is your C? Now you know that Fn rho by 2. So Fn rho by 2, and then V1 square d1 power 4. So V1 square d1 power 4 divided by 2 tan alpha by 2. So 2 tan alpha by 2, and then we have 4. So multiplied by 4, and then we have the remaining term 1 by d1 power 4 minus 1 by d2 power 4. Now what you are going to do, you are just going to multiply this value of d1 power 4 into the two coefficients, that is two terms. So when you multiply this particular value of d1 power 4 with these two cases, so finally what we have done. So let me check. Sorry. So next we are moving to the next step. So what I am going to do, now I am going to multiply this step, and I am going to rewrite this equation as well. So Fn rho by 2 v1 square, and then 1 by 4 2s are 8, right? So 8 tan alpha by 2. And finally we will obtain 1 minus d1 by d2 whole to the power of 4. So this is your delta P equation, final equation. So this is your pressure loss equation, and if you know the diffuser section diameters, and if you know the pressure coefficient, that is a moderate pressure coefficient for air, especially the wall friction coefficient, and then you know density of air is constant, which is the tunnel is operating in atmospheric condition, and then we know the value of inlet velocity v1, and then you know the duct angle alpha by 2. If you substitute all this term, you could be able to find the value of delta P. Now you have to find the coefficient also. So K, in the beginning I have told you about pressure coefficient, and then Q is nothing but half rho V square. So that is this term. So this term is getting neglected. And when you write other than this half rho V square, the term will be like F1 by 8 tan alpha by 2 minus d1 by d2 whole to the power of 4. Right. So this will be the finalized pressure loss coefficient equation for diffuser section. But when you are considering before diffuser section, most of the wind tunnel, especially in any kind of subsonic or supersonic tunnel, we have the convergent and divergent section. So before divergent section, especially for a section tunnel, we are considering test section. So when you are considering the test section, you are treating this test section diameter as d naught. So when test section diameter is added up, so this coefficient, that is pressure loss coefficient, will be rewritten as F1 8 tan alpha by 2, so 1 minus d1 by d2 whole to the power of 4, and then d0 by d1 whole to the power of 4. Just you are multiplying this term instead of multiplying with velocity ratio. So for this pressure loss coefficient, what you are doing is that when you are increasing the number of section in varying section or in any kind of diffuser, or diffuser means it may be act as a nozzle also. For a blow down tunnel, it acts as a nozzle, or for suction tunnel, it acts as a diffuser. Either it is converging or diverging. So if it may be a divergent section, the symbol carries like this. So the symbol carries like this. If it is going to be the convergent section, the symbol may exchanges. And then when you are going to increase number of sections, according to the equilibrium of velocity ratios from a discharge equation, that is Q1 is equal to Q2. Likewise, we have Q0 is equal to Q1. Okay, the same, from the same equation we can estimate it. So up to this we will end up this session, and then if you have any doubts or clarification, you may ask a query to our professor, and then we will get back to the class. Thank you.